Welcome to a webinar about intelligent wind farm operation. My name is Stella and I'm a consultant at GFI Consulting in the Department Energy and Utilities in Paris. So, how can you make your wind farm operations more intelligent? Our answer to this is anticipation. In the next 20 minutes, I will give you an insight into the two predictive solutions that we are currently developing with Opinum, namely the prediction of power output and predictive maintenance. Before we start, I'll briefly introduce GFI and explain how the partnership with Opinum came up. GFI is a digital services company that employs more than 27,000 consultants in 26 countries, where 10,000 of them are actually based in France, where GFI was founded. If you look at point 7, you can see that GFI is active in 7 different sectors, and one of them is energy, utilities, and chemicals, the one that our department is in. Regarding the revenues that you see on the left side, it's notable to say that 10% of those revenues were generated by energy-related projects, and our main clients in France are groups like EDF, Engie, and Total. Let's now look at how the partnership with Opinum came up. The partnership with Opinum is based on the idea to combine their expertise in data acquisition, storage, and visualization with our expertise in renewables and data science. You see, for example, on the left-hand side that we've been working with Nordex. This was on capturing and processing data from their wind turbines. And also regarding data analytics solutions, we've been working on European projects, for example, Electrific, which was about the optimal integration of electric vehicles. Now, going further to our agenda for today, I will begin with giving you a brief overview of the architecture used, and I will then continue going into use case 1, the prediction of production. For every use case that I'm presenting, I will give you a scenario of an example client and then show you the solution that was developed. So we see the same structure for use case 2, predictive maintenance, but here I will begin with showing you why you should use predictive maintenance to reduce your cost and in what way you should implement it to in fact increase your profits. So let's look at the architecture. On the left side, you see the different data streams that are being stored in the Opinum data app in the center. And on the right side, you see the modules that we are planning to implement on top of the Energy Data Hub. In the first box, you see tools that are focused on reporting and BI. And in the second box, you see the more advanced solutions. And you also find the two topics that we are discussing today, which are 1, prediction of production, and 2, predictive maintenance. Now that the architecture is clear, let's go into the precise use case, beginning with the prediction of production. In the scenario for use case 1, the problem of the wind power operator is that his predictions of wind power that will be produced are not very accurate. Thus, there's a difference between what he plans to sell and what he actually can sell. It's here visualized in the difference between predicted power and realized power on the right-hand side. As a consequence, he sees an increase in imbalance cost and opportunity cost due to suboptimal portfolio planning. By increasing this forecasting accuracy, those costs could obviously be reduced. I just want to make a short notice here, which is that this use case here is now focused on short-term prediction, but we are considering working on long-term predictions later on, because this could allow the optimization of long-term sales contracts, for example, power purchase agreements. But let's go back to use case 1. Before creating the model, we need to define the time range and the granularity. As we look at short-term forecasting, in this case, this should be in the next 24 hours and 30-minute time steps. As we just did, the model task is now specified, and we can then look at what's going in and out of the model. Predictions are made based on wind speed, temperature, humidity, and air pressure. and what is predicted is the power produced. As our model is based on weather variables, we can not only predict the output under normal conditions, but also with icing and under cut-off wind speed. So if we implement that, we have our input data on the lower left side, which is going into a random forest model, for example, and is then providing us with a prediction of power for the next 24 hours. It seems like predicting power output with a short-term model is easy. But if we now look again at our input data, we do observe that at optimal wind speeds and optimal temperature of about 20 degrees, we still have no power output. Why is this happening? The reason for this is that those downtimes represent planned and unplanned maintenance, something we do not include in our model so far. The only events that we can explain with our model are events related to weather data. So to include maintenance downtimes in our model, we need to integrate variables about the state of the machine. And this is where predictive maintenance comes in. Now, before introducing you to the second use case scenario, I want to remind you of the advantage of predictive maintenance compared to other maintenance strategies and how this is affecting your profit. In the first part of the slides, you see the estimated costs for staff, material, and downtime for the different maintenance strategies. Those are reactive, scheduled, and predictive maintenance. You also see how the risk is decreasing. This is because reactive maintenance is done when the failure had already occurred. Scheduled maintenance is done regularly and based on experience. And predictive maintenance, which is done before the incident occurs, based on pattern recognition. So in other words, you go from doing maintenance too late to doing maintenance too early, and to finally doing maintenance just at the right time. If we now look at the second part of the slides, we see how predictive maintenance can increase your profit. Like I said, it will be reducing your downtimes and also your maintenance cost. But at this point, we have to be realistic. The solution isn't as simple. Predictive maintenance can also increase your maintenance cost and increase your investment expenditures, because now you might be repairing or replacing earlier than before. So the challenge is really to find the right equilibrium. This is very well represented in the following graph. Here we see on the x-axis the different levels of maintenance going from low to high, and the y-axis the cost for maintenance. We see that we have high costs with insufficient maintenance on the left-hand side, but also with excessive maintenance on the right-hand side. Where we aim to go is to reduce costs in area B, what you find that we see in the middle, which is the optimal level of maintenance. So how do we get there? Obviously, we need to include maintenance costs in our model. And also, we know that if we want to assure a financial advantage of predictive maintenance, our total maintenance cost should not be higher than the cost for all consequences of a failure. What this means, in other words, is that if we want to guarantee financial profitability of our repairment replacement decisions in predictive maintenance, we need to extend it to an asset investment analysis over all of the asset's lifetime. But for now, let's go back to the situation of our example client and a simplified application of predictive maintenance. We can very well observe the unpredicted downtimes that we have identified earlier, as you see over here, and in the historical data, they are marked by this red drop in prediction. Because those incidences are not foreseen, they lead to downtimes of remarkable duration, and because delivery times for broken parts can be long, and a suboptimal approach regarding OPEX-CAPEX balance. In other words, we have to replace broken material now when it could have been repaired and therefore cheaper earlier. As I explained on the slide before, this problem should be addressed by creating a more complex solution and extending it to an optimization of a wider scope, in fact, over the whole lifetime of the asset, using something like asset investment optimization. But I think we all agree that this is not something I should explain in the remaining 5 minutes. So therefore, let's go back to our simplified use case, where we only want to detect a failure in advance. To design the model, we need to go back to our client to collect more information about his particular situation. Namely, we need to clarify what component is the biggest cost driver, what approach should be used for this component, and what time range is needed. To detect the biggest cost driver, we consider the frequency, so how often an incident occurred. We also consider how much it cost us, and using this information, we can calculate the expected cost. And we find that in our example, the highest costs are raised by the gearbox, which is not a surprise to you if you're working in wind power production, as they are very known for being maintenance demanding. And this is also the reason why Enercon is producing gearless turbines. So we know now that we want to focus on failures in the gearbox. Next, we need to define the right approach for this component. There are several solutions available, the analysis of oil, temperature, noise, or vibration. And if we consider how early this information is available before a failure, we see that vibration seems quite interesting as it's available early in advance. Thirdly, we need to define what time range is needed, so we go back to the client, which in this case desires 14 days of anticipation. And to sum up, we now know we need to create a model that predicts gearbox failures using vibration analysis 14 days in advance. Now that we have defined the model task, we can have a look at the concept. Input data is vibration signals picked up from the gearbox casing. And as vibration analysis has been around for a while, the advantage is that vibration sensors work reliably normally and they are not extremely expensive. And another advantage of this method is that it's non-intrusive, meaning that we don't have to open up our machine. If we then look at the output, in use case 2, the output is a binomial variable. Means that we detect if there is a failure or no failure. Regarding the calculation, vibration analysis is often done in frequency domain. This signal, the frequency signal, is then passed to a machine learning model, which then returns the binomial output if there is a failure or no in the next 14 days. We believe that this is a promising approach, on one hand, as it's a well-established method to detect failures in moving or rotating machinery, and on the other hand, because GFI has already used this approach successfully, applied to engine failure detection. This was everything from my side. So just briefly summing up our main points, what we're developing at the moment with Opinum is a short-term solution for predicting power production and a basic solution for predictive maintenance. And in the future, we're planning to extend the power production prediction to long-term cases and also extend the predictive maintenance solution to a broader asset investment optimization. So thank you very much for your attention, and we are looking forward to speaking to you.